Well, what differentials is all about is we give a name to the dx and the dy's and all those others as well. We're going to call those differentials. Just to give them a name, okay? Dx is a differential, dy is a differential. All right. There's a relationship then also between the differential dx and the differential dy, and here's what it is. Dy turns out, if we're talking function of f of x, is our function of x, y equals f of x, then dy equals, here's what it equals. It's the derivative at x times dx. And do you want to know where that comes from? That comes from, basically, dy dx, isn't that another name for the derivative? If I multiply both sides by dx, what do I get? Dy equals f prime times dx. Okay, that's basically where it comes from. It's pretty simple, pretty straightforward, and we'll talk about some other things in just a second. All right? So let's find dy. One thing we can do is find the value of dy for whatever function you want. F of x equals, let's do the square root of sine x just to make it really fun. Okay? Find dy for f of x equals square root of sine of x. Well, here's what dy equals. Dy equals f prime times dx. So what is that in this case? Well, f prime, what is f prime? You know, you might better say that's sine of x to the 1/2 power, right? Then use the chain rule. Chain rule says bring down the power. Sine of x to the 1/2 minus 1, so it'll be negative 1/2, times what? Derivative of the inside, cosine of x. Derivative of the outside, so the 1/2 power times the derivative of the inside. With me? So dy is going to be that times dx. Whoops. There you go. All right. And really, the next thing we'll do, we'll actually get numbers here plug in. All right. So let's say x is x is 0.5 and dx is 0.1. What's dy then for these? Well, once you have dy in these terms, then it's just plugging in, right? Dy would be 1/2 times sine of 0.5 to the minus 1/2 times cosine of 0.5 times dx, which is 0.1. And then it's just getting the numbers, okay? Let's see. This will be 1/2. Well, that's a fun one. All right, so sine of 0.5 to the negative 1/2. Why did I make my function so complicated? All right. This turns out to be, I get 1.4444. Cosine of 0.5, 0.877. 0.878, then times 0.1. So all that together. 1/2 times 1.444 times 0.878 times 0.1. 0.066, 0.0063, something like that. Okay. So really, dy and dx are just numbers. Now, here's what those mean. Is that okay? Did anybody else get this? Just to make sure I did that right. We'll go with it. Okay. All right. Here's what that means. The geometric meaning of dx and dy. Okay, so let's say I have some function of x. All right, and then I'm coming in here at some x value, and I'm going to draw my tangent line there. Somebody tell me what dy dx is to that. What does dy dx mean there? What's the geometric meaning of dy dx? Isn't it the slope of the tangent? It's the slope of the tangent. Okay? Well, how do we interpret sometimes slope? Isn't slope the rise to the run? So, if the slope is rise to run and it's dy dx, what is dy? Dy is the rise. Dx, that's the run of your tangent line. Okay, so if I want to, for slope you go from one point to another point, so let's just go out there a little bit. Go from that point to that point. And so wouldn't this from here to here, wouldn't that distance there be dx? Huh? And this, what would this be? Wouldn't that be dy? Okay, so that's, usually we do rise to run, so that's dy and that's dx, but also we could put that over there. Okay? All right. There you go. Now, to kind of throw a little more here at you. Well, you're with me on that so far. Okay. There's a relationship also here. We can do some more kind of approximating, if you will, but let's also talk about delta x and delta y. Delta x and delta y is, the delta symbol. Sometimes you've probably seen that before. Change in x, change in y. That's what those mean. So delta x and delta y. Now, these have more to do with the actual curve. This here we're talking about the tangent line. Delta x and delta y are more to do with the curve, your actual function graph. Okay, so we're back to this. Well, if you look at that, there's obviously a connection here between your dy there, and then this with that point, and then your curve from that point to that point. What is the connection? Well, if you'll notice there, delta x being the change in x, delta x would be, the change in x would be this, wouldn't it? So delta x and dx are equal. They're one and the same. Now, delta y, the change in y, though, is only this much in this case. You with me? Because that's how much I've changed in the y direction for the function. So delta y and dy, they're slightly off. There's a slight difference. Okay, but they're pretty close. I mean, I went pretty far out here. You're usually not going that far out for your tangent line. So, you know, your dy and delta y. dy is close to your delta y. But anyway. What are we going to do with all that? Well, one thing is to know the picture there. Change in x, change in y, delta x, delta y, what dx and dy are. Well, what we're going to do is we're also going to compute some dy's and delta y's. We already did one dy. Let's talk about delta y. Delta y being the change in y, here's what it works out to be in the formula form. Now let me explain. Delta y is the function f evaluated at x plus delta x minus the function at x. That's the change in the y-values. Why is that? Well, look at this. F of x, that would be this much. It's the function at x. X plus delta x, well, isn't this x plus delta x right here? So this other point is f of x plus delta x. So delta y, this much, is take the difference of those two. That's all it is. So here's your formula for delta y, dy. We had that earlier. It was f prime of x dx. We're going to compute delta y and dy for a few functions on the homework there. So let's do one here. Example. All right, so find dy and delta y for f of x equals x squared plus 5x minus 6 at x equals 2 and delta x equals 0.1. Let's start with dy, since that's the first one I wrote there. dy is just f prime of x times dx. Okay, well, f prime of x is easy. F prime of x just be the derivative of 2x plus 5 times dx. Now, in this case, we do have numbers to plug in, don't we? I have an x value. So they do want you to compute a number here. It'd be 2 times 2 plus 5. And we actually do have a value, even though it's not specifically stated. We do have a value of dx. What is dx? I don't have it given, but I know what it is. What is dx? Yeah, delta x equals dx, vice versa. So if delta x is 0.1, then what is dx? It's also 0.1. Those two are the same because, you know, go back to the picture there. Delta x and dx are always equal. So delta x is 0.1, dx is 0.1. So it's, what is that, 4? So dy would be 4 plus 5 would be 9 times 0.1. That's 0.9. dy is 0.9 in this scenario here. All right, delta y. Well, delta y is f of x plus delta x minus f of x. What does that work out to be here? Well, f of, x plus delta x. X is 2, delta x is 0.1, so x plus delta x would be 2.1. Minus f of x, that'd be f of 2. So I'm just, for delta y, I'm just going to do f of 2.1 minus f of 2. And that is the function value 2.1 at 2.1 and function value at and so f of 2.1, just plug in 2.1 right here, right? Be 2.1 squared plus 5 times 2.1 minus 6, whatever that gives you. 2.1 squared plus 5 times 2.1 minus 6. I get 8.91 for f of 2.1. F of 2, well, that's just plugging in 2. That would be 4 plus 10 minus 6. 14 minus 8.